Welcome back to G Fun Facts Online, the podcast that dives deep into the most mind-bending corners of science. Today, we're asking a question that might just flip your entire understanding of reality upside down. What if the very fabric of space and time, the stage on which our universe plays out, isn't fundamental at all? What if it's an illusion? Or, more accurately, an emergent property, born from something even weirder and more fundamental, quantum information. Strap in, because we're exploring how spacetime itself might emerge from the quantum realm. Okay, so when I say spacetime emerges, what do I mean? Think about water. You know water is fluid, right? You can pour it, swim in it. But is a single H2O molecule fluid? Nope. Fluidity is a property that time emerges asterisk when you have billions and billions of H2O molecules interacting. Physicists are now exploring the idea that spacetime is like that fluidity. It's not a basic building block of the universe, but something that appears from the collective behavior of countless tiny, underlying quantum bits and their interactions. The very geometry of our universe, its shape and dimensions, might be woven from the entanglement patterns of these quantum constituents. So what's doing the weaving? A prime candidate is one of quantum mechanics' most famous and bizarre features: quantum entanglement. Einstein called it spooky action at a distance. It's this incredible connection where two particles can be linked in such a way that they instantly influence each other, no matter how far apart they are, across the room or across the galaxy. The wild idea here is that entanglement acts like a cosmic superglue, stitching together the very fabric of spacetime. The more entangled different quantum systems are, the closer they effectively become in this emergent spacetime. Entanglement isn't just happening in space. It might be asterisks creating space. This isn't just a wild guess. There are some pretty solid theoretical frameworks pointing in this direction. You might have heard of the holographic principle. It's the mind-boggling idea that all the information contained in a volume of space, say, this room, or even the entire universe, can actually be described by a theory living on its boundary, like a 2D surface. Think of it like a 3D hologram projected from a 2D film. Our universe could be a grand, cosmic hologram. A powerful example of this is something called the ADS-CFT correspondence. It's a bit of a mouthful, but it basically shows a direct mathematical link between a theory of gravity in a certain kind of higher dimensional spacetime, that's the ADS part, and a quantum field theory without gravity in a lower dimension, the CFT part. What's super exciting is that this correspondence has revealed deep connections between entanglement in that lower dimensional quantum theory and the geometry of the higher dimensional spacetime. There's even a formula, the Ryu-Takayanagi formula, that directly relates how much entanglement there is in the boundary theory to the area of surfaces in the spacetime. More entanglement means more space. Now here's where things get even more surprising. Imagine you're building a quantum computer. One of your biggest headaches is protecting the fragile quantum information from errors and noise. Scientists developed something called quantum error correction to do just that. And guess what? It turns out that spacetime itself seems to behave like a quantum error-correcting code. This means that information about what's happening in the bulk of spacetime, our familiar 3D world, is encoded redundantly in the underlying quantum system, perhaps on that holographic boundary. This redundancy is crucial. It could explain why spacetime is so robust and stable, why it looks smooth and classical to us, even though it might be emerging from a messy quantum world. It's like spacetime has its own built-in backup system, and the connections don't stop there. There's a fascinating conjecture called ER equals EPR. EPR refers to Einstein, Podolsky, and Rosen, who first highlighted the weirdness of entanglement. ER refers to Einstein-Rosen bridges, which are more commonly known as wormholes. The ER equals EPR conjecture proposes that these two seemingly different concepts are actually two sides of the same coin. It suggests that any two entangled particles are, in some sense, connected by a microscopic wormhole. If true, this provides another incredibly direct link between quantum entanglement and the very structure of spacetime. We've talked a lot about entanglement. There's actually a way to measure it, called entanglement entropy. It quantifies just how much entanglement exists between different parts of a quantum system. And this measure, entanglement entropy, is emerging as a crucial bridge. Changes in entanglement entropy can directly correspond to changes in geometric properties, like distances or areas, in the emergent spacetime. More entanglement can literally mean regions of space are closer, or that space itself is expanding or contracting in certain ways. This even leads to some radical rethinking of Einstein's famous field equations, which describe gravity. Einstein told us that mass and energy warp spacetime, creating gravity. But some new theories propose that we might need to add something else to these equations, an informational stress-energy tensor. This new term would be derived from quantum entanglement entropy, suggesting that the curvature of spacetime, gravity itself, isn't just a response to matter and energy, but also to the information structure of quantum fields. Mind blown. So, why is all this so important? Well, if spacetime does emerge from quantum information, it could help us solve some of the biggest puzzles in physics. Take the black hole information paradox. What happens to information that falls into a black hole? Does it just vanish, violating quantum mechanics? Emergent spacetime ideas, particularly those involving holography and quantum error correction, offer new ways to understand how information might be preserved. More broadly, this research is a leading contender for the holy grail of physics, a theory of quantum gravity that finally unifies quantum mechanics, the physics of the very small, with general relativity, the physics of gravity and the very large. It would mean that gravity, one of the fundamental forces we experience every day, isn't fundamental at all, but an emergent phenomenon, perhaps like an entropic force, arising from the statistical behavior of underlying quantum bits. And here's a wonderfully unexpected twist. This deep theoretical dive into the nature of reality has forged a surprising link with the cutting edge of technology, quantum computing. The principles of quantum error correction, which are vital for building fault-tolerant quantum computers, seem to be the same principles that ensure the stability and coherence of spacetime itself. It suggests a deep, shared logic between the cosmos and computation. Advances in understanding one could directly propel advances in the other. Who knew that trying to understand the universe could help us build better computers, and vice versa? Now, it's important to say that these are largely theoretical ideas, and testing them is incredibly challenging. We're talking about effects that might only be noticeable at unimaginable energy scales or over vast cosmic distances, but scientists are brainstorming. They're looking for tiny modifications to how particles travel at very high energies, or slight deviations from known physical laws, or even faint quantum gravitational signatures in the cosmic microwave background radiation or in the ripples of gravitational waves. There are also big theoretical hurdles. The AD/CFT correspondence, our best model so far, describes a universe that's quite different from our own, which is expanding and accelerating. Extending these ideas to a more realistic spacetime, like our de Sitter universe, is a major ongoing quest. And we're still working to fully understand the precise nuts and bolts of how our smooth, classical macroscopic spacetime emerges from discrete quantum information. The ultimate goal? To derive Einstein's equations of gravity, or a more complete version, directly from the principles of quantum information. So, what's the big takeaway from all this? It's a potential paradigm shift in how we view reality. For centuries, we've thought of space and time as the fundamental stage. But this new research suggests that information, particularly quantum entanglement and quantum information, might be the true bedrock. Space and time, in this view, are beautiful complex structures that emerge from this deeper informational layer. It's a frontier that's pushing the very limits of what we know, connecting fields like cosmology, particle physics, and quantum computing in ways no one anticipated. It certainly gives you something to ponder next time you look up at the stars, or even just look around the room. Is what you're seeing really fundamental, or an intricate illusion woven from quantum threads? That's all for this episode of G Fun Facts Online. Join us next time as we continue to explore the wonders and mysteries of our universe. Don't forget to subscribe, and thanks for listening.